gotta start. It's late. Okay, hello everybody. How are you doing? Good? Great? Alright. So I'm looking forward to our session today. I'm going to turn down the volume a little bit because it sounds a little loud to me. Okay. Administratively, what's going on in the class? Yes? The exam is in 1 week. All right. So, and what are you bringing to that exam? What? Okay. Okay. Maybe. Hopefully not. What are you bringing to the exam? That's legal for the exam.
Formula sheet.
Yeah. How many?
1 double-sided page.
2. 2 double-sided pages. Okay. So you can bring. So guys, folks. All right. There's been some talk. Okay. That it'd be great to have. We're going to have lots of time to talk together. That's what I love about being a student, or being now not a student, but kind of a student. All right. When we're in this part of the class, so please, so that other people over here, other people over here. All right. So yes. So what's the deal? How many formula sheets? 2. Front and back, 8.5 by 11, or A11, is it? A14? No, A11, I think. Whatever the closest one is to 8.5 by 11 inches. All right. Write whatever you want on it. Okay. I think this time in particular, with an emphasis on Moore's circle, right? I would write down some examples of how to do Moore's circle, right? I would write down also how to do the equilibrium on a triangle, okay? And guys. Okay. So and I also I would write down information about torsion. Okay, we didn't really do angle twist last time. Okay, and so be comfortable with both calculating shear stress and calculating out angular displacement in those cases. The combined loading, that's the one session I missed with you, and it's critical, and we're going to go through some of it today, okay? But that is pretty key, right? So if you're given a rod or a rod beam-like structure, coming out of a wall, you want to be able to handle what the shear from torsion might be, what the transverse shear might be due to bending or some type of transverse force, some type of transverse shear force internally, right? And also, of course, be able to calculate bending stress and axial loading. Don't forget axial loading as well. Okay, that's maybe a simple one to forget. Okay, but that's still often part of the game. Any questions? Okay. Yes, Kevin.
So for this specific exam, is a lot more of the focus going to be on the materials covered after exam 1, or an equal mix of exam 1 material and exam and whatever?
It's going to be more of an emphasis on stuff since exam 1, right? But we had, like I was saying, we didn't really cover torsion on exam 1. Okay, we had the same kind of deal, except we kind of went 2 lectures before not covering. But yes, material from them. Today is the last day of content that is eligible for the exam. And unlike exam 1, I'm pretty confident that the stuff we covered today is going to be on exam 2. Okay, because we're going to talk about absolute maximum shear stress. Okay, and sometimes it's a little awkward when you'll see today why it can be awkward just to emphasize the importance of in-plane maximum shear stress, okay, versus absolute maximum shear stress. Because the one that really dictates whether or not something might fail is the absolute maximum shear stress. And sometimes the absolute maximum shear stress is the same as the in-plane maximum shear stress. Okay, but it's still nicer to know, okay, this is the absolute maximum shear stress. There was a question over here.
You might go over the format of the exam.
So yeah, it's going to look very similar to the exam from the summer, the exam from the previous spring, yeah, and the exam from course, those exams are plus more are available on the website. I would start, I said it last time, start with the more recent exams and work backward, okay? Don't start with 2015. All right, you can, all right, but I would start with stuff that's more recent. That's probably more of the style we come to accept for these exams. Okay, any other questions? Okay, so the assignment that we have from today's message, okay, or from today's session, will be due on Thursday. But then what we have on Thursday, I still encourage you to show up. But that stuff is not due until after Thanksgiving. Okay, so that will be due the Tuesday after Thanksgiving. So you have a nice long time to think about things. All right. So let's go ahead. So what are we going to talk about today? We're going to first talk about something called triaxial stress, or a condition of triaxial stress. And for one or two, the people that came to office hours are like, hey, do we have to do eigenvectors and eigenvalues and that? It's like, okay, not really, okay? But this is like for your good to know file. And when you take the graduate class on mechanics, or a more advanced class on mechanics, or aerospace structures or aerospace materials, you'll be like, oh yeah, I remember that thing about tensors. Okay, so you can be like, oh yeah, I've heard of tensors, even though I don't really know what the heck to do with a tensor. Okay, so we'll talk about triaxial stress, and then we'll get into calculating out absolute maximum shear stress with more circle. This topic is important. It will be on the final. It will be on most likely on Tuesday's exam. Okay, so. If it doesn't quite gel, right, ask questions or revisit and work on the problems, or ask your neighbor when it's time to ask your neighbor. And then the final thing is that we'll say, okay, here's a structure, okay? And now if you've got a material element on that structure, how do we calculate the absolute maximum shear stress on that element at that location, all right? So first, a couple of slides that are kind of review. Do you remember this? We said that we could depict state of stress with 6 parameters, okay? And we call these sigma x, sigma y, sigma z, tau xy, tau z, tau yz, all right? And we can also put these in a 3x3 matrix, which we call a tensor. What is a tensor? You can watch this nice YouTube video, okay? But essentially, even though we talk about different states of stress or different conditions of stress, okay, as we orient or as we transform or rotate an element at a particular location, the information is all preserved, right? If you rotate by 45 degrees and rotate by 15 and by 5 and 6 and whatever, right, you can eventually work your way and figure out, okay, this is what, I mean, this is the state of stress at this particular orientation, but this is the state of stress at that location. So that's what makes a tensor, or one of the things that makes a tensor. Okay? And then, as you recall, we can put these states or these stresses on the faces of a cube, all right, of a material element. Now, one thing also to keep in mind, remember, we've talked about beams in particular, and we do method of sections. And when we do method of sections, right, we say, oh, look, there's this internal shear force, okay? Or we say, oh, there's this normal axial force, okay? If we took a slice there on, in that face, and we say, oh, there's the shear force, right? Or there's the axial force coming out of that internal surface, that would correspond to what we call a traction vector or a traction force, okay? The stress is the sigma 1, sigma 2, or sigma x, sigma y, sigma z, right? All these in the taus. These are stresses. Of course, they're not forces, but these are essentially dot products of that traction vector with the x, y, z coordinate system, and then divided by the area, okay? That's how you can kind of think of, I know this is a little bit abstract, but that's how you can kind of think of, oh yeah, there's that shear force internal on a face, And if I think about it at this location, and then I do a dot product with the vector that I'm interested in, I'm going to be able to get, you know, the stress. Okay, so these traction vectors, okay, let's do this. Okay, these are traction vectors. See, like this T, right? So that's kind of like, imagine an internal shear force or an axial force. But then we have corresponding, okay, sigmas, all right, that are stress components that are based on this traction vector, but dotted with like an E3 or E2 or an E1 to get these relationships. Now, the stress tensor, and then you can look up Cauchy stress tensor if you like, okay, has this form. We've also seen that this form can be a little bit confusing when we do finite element analysis, right? And we had to, in some cases, look at the shear strains and be a little bit careful about them. Those are the strains. These are of course the stresses. But the stresses, okay, they map very nicely over to what we've been using here. Any questions up to this point? This is kind of a review. And you can go back to session 3, I believe. It's when we started covering stress and strain. Now, what's next? We said, okay, just a second ago, right, we can have this kind of interesting configuration of stresses, conditions of stress on an element, okay? And that's really neat, that's cool, right? That can be very confusing, of course, right? If you've got like all these shear stresses, sigmas, you know, it's like, whoa, what's going on this element, all right? Maybe it's not that confusing. I mean, they're really only 6 components, right? But what's cool is just like we have done with a 2D square, we can also find a 3D orientation, all right? So remember, we're finding the principal stresses, right? So you've got a 2D state of stress, what we call plane stress, and then we rotate by some amount, and then voila, all the shear stresses disappeared, right? And that's the state of principal stress, or principal stresses, okay? So same thing happens in 3D. You can start with a state of stress on an element like this, okay? And we can rotate by one or two axes and find a state of stress, okay, that only has the normal stresses coming out of it, or only has principal stresses coming out of it. Okay? So this is obviously a little bit easier to understand, right? It's like, oh, okay, I got axial stresses, I can kind of think of that, right? So my taus go away, and my tensor ends up looking like something that has sigma 1, sigma 2, and sigma 3, okay? And it's just going to put them on the main diagonal, as you see here, okay? And the other components, those are going to be zeros. And of course, those other components would be the shear stress. Okay, so would I ask you to do this? Kind of, maybe, sort of, okay? Because we're going to use more circle, essentially, to look at some of these 3 stresses, sigma 1, sigma 2, sigma 3, okay? And we're going to, and if I start with a plane stress element, okay, it's actually not that hard to do. Okay, the convention that we follow, and I kind of got the convention flipped, all right, this afternoon when I was typing out in the group meeting. It's like, oh, sigma 3 is, or I said sigma 1 is equal to 0, right? Actually, usually sigma 1 is the largest, sigma 2 is next in line, and sigma 3 is next in line. Okay, so sigma 3 is often 0, especially when we're dealing with a case of plane stress. Which direction is sigma 3 in that case? Well, if it's an x, y, right? If it's x and y, then sigma 3 would be in the z direction. Okay, and that's often 0, especially when we're dealing with the thin-walled pressure vessels. Okay, so now this is a method to find principal stresses in 3D. You would not have to use this method on an exam, okay? You would use more circle on exam. But nonetheless, I think it's good to get exposure to this, so then once again you're like, oh yeah, I know how to kind of manipulate tensors. I know how to do a little bit of this, right? So our goal is to go from this general state of stress where we're assuming that we have non-zero taus in the tensor, and we want to get sigma 1, sigma 2, sigma 3, and zeros everywhere else. So what you do, or one way to do it, okay, is you calculate the invariance in an eigenvalue problem, okay? Don't worry, now it's just jargon, all right? But if you do linear algebra, there's this is like A lambda equals I, and then you figure out, okay, these invariants, okay? And I would be that column vector. So anyway, so what you can do is you can calculate I1, I2, and I3, and sigma, see this is what order? This is a third order polynomial, right? So how many roots would it have? Three roots, right? Which is good because we need three. We need a sigma 1, we need a sigma 2, and we need a sigma 3. Okay? So the math works out that you can get your three components by solving for the roots of this equation, where I1, I2, and I3 are these invariants, okay? And if you then take, what's cool, all right, once you have these principal stresses, you'll see in a very brief moment, it's very easy to draw the Mohr circle. Once you have sigma 1, sigma 2, sigma 3. Very easy to draw Mohr circles. More circles, I should say, because now we're going to have multiple Mohr circles on our sigma tau plot, okay? And then if you've done that, we can figure out what the maximum shear stresses would be in those given planes. So what we're saying is, okay, I started with sigma x, sigma y, I started in the x, y, z coordinate system. I've now rotated somehow, okay, and we're not going to care too much about what those angles are. I've rotated somehow, and now I have a 1, 2, 3 coordinate system, right? Sigma 1 is one of the coordinates, or sigma 1 is in the 1 coordinate, sigma 2 is in the 2 coordinate, sigma 3 is in the 3 coordinate, right? And of course, they're orthogonal, okay? But I don't necessarily know what they are. Okay, I don't know what those orientations are necessarily to what I just described in x, y, z initially. Okay? If you go back to the linear algebra, okay, and you really wanted to know those directions, which is not necessary for this class, we're solving for the eigenvalues, which are sigma 1, sigma 2, and sigma 3. Okay? The roots of the invariants. But the eigenvectors, okay, those eigenvectors actually happen to describe the directions of sigma 1, sigma 2, sigma 3. And we don't care about it for now, okay? Not now. Any questions on this? Any questions? Yes?
Can we get the problem like that on the exam?
No, you can't get a problem like this on exam, okay? You cannot. I cannot do that, all right? Those are like one of the first phrases of our oldest child. You cannot do that. It's like, oh, what kind of parents are we? All right, so yes, Kevin.
So sigma 1, sigma 2, and sigma 3, those are the eigenvalues of the linear algebra system. But
yes.
In the same context, what is I1, I2, and I3?
Those are called invariants.
Okay.
And so when you do the eigenvalue problem, you can have like an identity matrix, or you can have, actually, no, yeah, I'm wrong. No, they're just invariants. I'm wrong. Just let it be. They're just invariants, okay? Yeah, sorry. Okay, now, I want to show you something here, okay? When we do this example, all right, okay, so let's say we have sigma x equals 100, sigma y equals 50, and tau xy equals 10 megapascals, all right? The other stresses are 0, all right? And so we're going to use the invariance of the eigenvalue problem to find the principal stresses, okay? So, we can go ahead and we can draw out Mohr circle, all All right, that's all fine, right? But and that depicts a state of stress. That's all happiness. All right, that's all happiness, no problems. Okay, and we can find sigma 1 and sigma 2. Okay, doing this. If we want, all right, so if you go, let's see here. Whoops, I don't want to do that. Okay. Just so that, because you will get, so even though it's not fair game for the exam, it is fair game for the homework. Okay? But don't sweat. Don't sweat, because it's not going to be that bad. Okay? If you go down, okay, to the collab that's available, right here, okay, 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 password reset started. Ooh, that's dangerous. Okay, I don't want to do that. All right, well, I'm going to go ahead and I'm going to run this first, right? We know how to do this. And essentially, all you've got to do... Oh, sorry. Sorry, thank you, Chris. That was you, Chris, right? Thank you. A different Chris is saying you're welcome? Nice, guys. All right. Thank you. Thank you for keeping it down, guys. I appreciate the lower decibels. Okay. So what you do, okay, is you just plug in, all right? You're just going to plug in for sigma x, sigma y, sigma z, tau xy, right? You're just going to plug in the state of stress here, okay? And you're going to let collab run its magic. So in doing that, all right, so this is the tensor, right, that you have. And then what we're going to use is the eigenvalue solver, all right, from linear algebra that's embedded. Or you've got two ways of looking at this. Whoops. Okay, you can also use the invariants. Okay, these big formulas, they're all there. So there's no reason to type them out again, all right? And I know some of you love MATLAB. MATLAB is great. I spent many years using MATLAB, okay? So if you really want, you can copy and paste this into MATLAB, all right? Why? Because all you got to do is hit Control Enter, okay? So you or hit the green or hit the little thing, right? So you hit it and see, look, it tells you what the principal stresses are, okay? It does that calculation for you, all right? So in case you ever want to, you know, someone says you're on the subway, right? You're on the Metro or New Jersey Transit, and someone says, hey, I got a tensor here with sigma x equals this, sigma y. You just pull up this collab, and you're like, I know how to figure out the principal stresses, man. Or woman, or person, all right? So, I mean, don't you think this is useful? Okay, yeah, right. No, why is it useful besides being a smart aleck on the subway? Why is this stuff useful? Yes, Federico, are you recovered? Oh, okay, well, I miss you down here, but yes, what's up? Why is this important? The collab? Oh, yeah, okay, why is why is the collab? Why is calculating these principal stresses important? We've been doing this now, right? And I probably, is it my fault? It's my fault, okay, it must be, all right, it must be me. All right. The reason you don't know why this is important is my fault, okay? Some materials, the brittle materials, the ceramics, they fail because of maximum normal stresses. And what are the maximum normal stresses? The principal stresses, okay? So you can have an interesting state of stress, okay? And you're like, oh, if it's a brittle material, is it going to fail? And the way to answer that question is, I got to calculate the principal stresses, and then I got to do some other stuff we'll talk about soon, but in a couple of sessions. Okay, but the criteria for the criteria of failure. But the short story is, these maximum normal stresses are what are going to sink you. Okay, and so you want to make sure that you can calculate them. If it's a ductile material, hey guys, come on. Okay, so if it's a ductile material, all right, then like the steels, most of the steels not cast iron. Cast iron is brittle actually. Okay, but most of the steels are going to be ductile. We don't care about Bruno. We don't care about the principal stresses as much as we care about the maximum shear stress. Okay? And today's session is all about absolute maximum shear stress. So now when you're on the subway and says, oh, I want you to calculate the principal stresses, you'd be like, do you know why the principal stresses are important? And they'd be like, maybe. Okay, and then you can explain to them. It's because you're trying to figure out if it's going to break or not. And then you'd be like, hey, then you're like, oh, look at this pole. No. Actually, look at this fuselage thing that we're in. I think the principal stresses are really high. And then you freak out everybody and say, oh, we're going to crash and die. Okay? No, so that's not, that's not a good idea. But I have, one of my mentors, he was a professor, and he did a lot of consulting. So one time he was on a plane, and he was flying, and he's like, something's wrong with those jets, the engines. Right? So he's like telling the flight attendant or something, you really should get these engines checked out because there's an issue. Talk about freaking out everybody on the plane, right? So that can happen. And I used to show in DMC. I used to show this old movie. Anyone know who Jimmy Stewart is? Like the old Jimmy Stewart? He's passed for black and white movies. Huh? Yeah. Oh, not the driver. No. Not the race. Not NASCAR. Okay, this is a different. No. Yes. Maybe. Yeah. So I think the movie's called No Highway in the Sky or something like that. So, but he's in a bunch of different movies. He's a big movie star, right? Like the biggest movie he probably, or the most memorable one for many people, so it's called A Wonderful Life. All right. So anyway, but he is this engineer on this plane, and he's freaking out. Okay, and he's making other people on the plane freak out too. Okay, so he's like, how many hours has this engine been running? Or is plane been flying? Yes. Yes. Yes, now you know. Okay, yes. Okay, good. Okay. Yes. Okay. Good. So that's how we calculate out the principal stresses, and on your homework, okay, you'll get to do this, right? So all you got to do for your homework is use the code, plug in these principal stresses, or plug in this theta stress, better said, and then you get the principal stresses, okay? All right, why don't we take a few moments, though, to let you do that, because we have time today. I think we have time. So take 5 minutes, talk with your neighbors, and do it. It's very sad. We're without our beloved TA, Praj. I hope he's okay, but he is at home, hopefully having some nice hot water or something. Okay? So, yes, you have a question? Yeah.
I need to get better by this week. I can do it Monday. Sunday afternoon into Monday.
Yes. Oh.
Yeah, those are not or I don't know. But change the lunch was something. No drinking. Yes. Damn, I mean, that's a superpower.
Wait, can I see?
Yes. Yes.
You see you driving.
No, for question, but it says they're all the same.
Sixth. Sixth.
Principal stresses, and then we can do others.
No, you would. Just plug it into the system. It's a long process. The second one, you just plug in the number.
Q2. Question 2 is similar, but you need to find
From exam 1.
variance of time maximum principal stress. Don't worry about the stop.
How's it going? Any luck? Any luck on getting the principal stresses? Sorry, I should probably.
Are you doing this all up? Like, are you writing the Python for it?
Did I write it? Yeah, I wrote it.
Like, for all the questions?
Yeah, I wrote the co-op.
Yeah.
Yeah, I mean, but I'm not, did I make up these equations? No, I didn't make these equations. Huh?
There's no point in saying doing it if you're just in that.
There's no point in you doing it.
Yeah.
I'm just trying to expose you right here, okay? In other cases, like for the session 18, or the 17, we had to rotate, right? You had to know that element, you had to, we're doing a rotation of x, right? And everyone's like, oh, yes. So you put the pull-out, you had to use a rotation matrix for x instead of for z. I don't think anyone actually did it. I think everyone just said, oh, that's nice. Okay. How's it going? Did anyone get it to work? Yeah, Max, did it work? You just plug it in and it worked? You're doing it in Desmos? That's fine. I like Desmos. I'm not allowed to, I don't think I'm allowed to prescribe it unless I pay for it. At least that's what I read. I was like, I considered using it, but then I was like, oh no, they let you use it, they let everyone use it, but if you use it in class,
How are they gonna know?
everything's online. In this class? Alright, I could be wrong about that, but yeah, Desmos, I'm not quite sure how to do this in Desmos though, because you have to have, I'm sure Desmos has a way to do it.
It has the sliders.
Sliders.
So I don't have to worry about that.
You do not have to worry about the
For this class?
for this class.
So, question 2 has 25. Question 2,
Use the collapse.
how did you use question 2? Oh, it's the same thing. Yeah. It's the same thing, all the, all 6 tensors, abundance.
Alright, that sounds like a lot of work, but kudos to you. Kudos to you, alright? Anybody else get 5 or 21 or 20, question 1 or question 2 from section 20 to work? Yeah, alright, yeah, Keisha, one, okay, yeah, okay, good. Is it okay if we move on now? Alright, let's move on. Okay. This, if you were asleep, I invite you to just wake up because this is important stuff, all right? Okay. And this is a little bit of a mind bender. Let's say we have the principal stresses. Okay? Let's just say we've got sigma 1, sigma 2, sigma 3. All right? And we're going to say this is for in plane, which means that the normal stress coming out of the blackboard at me is 0. Okay? Now, okay, so that means sigma 3, that's going to be the lower one, the smallest. That one's 0. So we really have sigma 1 and sigma 2. And let's say that sigma 1 is aligned with the x-axis. Okay? Like this. And sigma 2 is aligned with the y-axis. All right? Everyone's got this image? Super easy peasy. Okay? If I draw the Moore's circle, okay, it's going to be a circle. Okay, so like circle. All right, and what does it look like? It looks like this, right? Everyone agrees with this? Sigma 1 is something, sigma 2 is something. Easy peasy, lemon squeezy. Okay, now, and I did draw the sigma 3 here, right? So now, like, what oh, sorry, you can't see. It's there. I drew a sigma 3 here. So this is like a little bit, like, what's going on with that? Now, let's rotate our perspective. What are we doing? What do we do? We rotated 90 degrees about y. Okay, so the y-axis, right-hand rule, 90 degrees. That means what? That x that was on the right side is now into the board. Okay? And now we just look at the state of stress in that plane. Okay? And what do we see? Well, we see the sigma 2 still. Okay, we see the sigma 2 still. But sigma 1, which was in the x direction, has vanished. Okay? It's just vanished. It's there, right? But I don't see it in that plane. But if I were to draw this circle, okay, if I draw the Moore's circle, just by what I see here, what does it look like? Well, the sigma z is 0, right? Sigma 3 is equal to 0, so it's just going to be the circle here. Okay? Like this. Okay, everyone see that? But you're like, wait, it's the same element, but you just drew 2 stinking different circles. Okay? Same element. Now, let's say that we take this state of stress we had initially, and we rotate 90 degrees about x. So now the z, okay, 90 degrees, and then in this case, it's negative 90 degrees, right? So we went negative 90 degrees, so that the z coming out is now pointing up. The y that was pointing up is into the board. Okay, so this is minus 90 degrees about x.
Wait, which one did we rotate about?
So this one, well, you tell me, what did we rotate about to get to this state? Oh, wait a second. Yeah, I see where you're confused. Yeah, no, so this one, yeah, we rotated about y. Yeah, that's all. We rotated about y, 90 degrees. Okay? No, I don't see what, yes?
I don't understand what, there is this stress 3. It doesn't appear on the sketches of the left, it does appear on the sketches of the right.
Yeah. So, okay, good question. So, sigma 3, all right, if this were the, don't look at everything else. Okay? What is sigma 3 in this picture?
I don't know.
Zach?
Would be the stress in the z direction?
Yeah, it's a stress in the z direction. Remember, sigma 1, the principal stresses have to be orthogonal to each other. Okay, so you only have one choice here because you've got 1, 2, 3. Okay? That's it. They have to be orthogonal to each other. Okay? So sigma 3 is coming out of this plane. I've drawn it here, but the way we used to draw, remember we've only done Mohr's circle up to yesterday, or up to Thursday. We've only done Mohr's circle on 2D plane, okay? So now what we're talking about is, wait, maybe there's something else going on in another dimension, right? And so what we're trying to show is that just by rotating this state of stress, okay, which is actually planar, right? Because it's just sigma 1 equals something, sigma 2 equals something, and sigma 3 is equal to 0, okay? We're able to get what look like different Mohr's circles, okay? Because we're just rotating and we're ignoring, because we don't draw them coming out of the element, we're ignoring them, and they are going to be coming up with, we're going to be having these different circles. Okay, so like this one, there's only a sigma 2, and sigma 3, if you want to think about it as in the z direction, right? Sigma 3 is in the z direction, as we said before. That's this one, it's 0. So that's the Mohr circle corresponding to this one. And then, if I rotated about x in the minus 90 degrees, like we were talking about, then, minus 90 degrees. So z, which was coming out at us, is now pointing upward. Sigma 1 is still there, okay, but we've hidden now sigma 2. Sigma 2 is coming in and out of the plane. That Mohr circle, what's it going to be? Because sigma z is sigma 3, which is equal to 0. It's going to go between these guys, sigma 1 and sigma 3. Okay? Like that. Everyone see this? So, last week, when we said maximum in-plane shear stress, and I gave you this planar element, what did you say? You came over to this red circle, and you said, that's the maximum shear stress. And we call that maximum in-plane shear stress. But now, we've got a 3D depiction. We've just rotated the elements. We've just rotated the element. What is the maximum, absolute maximum shear stress in this case? Which circle does it correspond to? The red, the purple, or the orange? The orange, right? It's now down here. Okay? So it's the same state of stress that, or one of the same states of stress that we've been talking about, but the absolute maximum shear stress is based on what's happening in all 3 dimensions. And so when you do this problem, what you do is you say sigma 1, sigma 2, sigma 3. You plot them, and then you just draw all 3 of these circles. And if you're interested in the maximum in-plane shear stress for any of them, so if you're interested in the maximum in-plane shear stress for the 1-2 plane, well then it's here. If you're interested in the maximum in-plane shear stress for the 2-3 plane, it's here. If you're interested in the maximum in-plane shear stress for the 1-3 plane, it's here. If you're interested in the absolute maximum shear stress, it's here. Okay? There was a question upstairs. Federico? Okay, you look at the next slide. All right, great. Okay, so this is the tau max xy, tau max yz, tau max absolute is this one. Okay, any questions? All right, so this is, once again, remember, maybe it's becoming more clear. I can use the, this is actually, how do I say this? I can use the tensor map, right, to try to figure out where I have maximum shear stresses. Or I can just use Mohr's circle, right, to figure out what the absolute max shear stress is or what the maximum in-plane shear stresses are. Mohr's circle is much simpler. Okay? And this is one of the powers of Mohr's circle. Okay, now, we did all that, but there are formulas, all right? So you're gonna write these down, and you're gonna probably not use Mohr circle in some cases, but I encourage you to at least know what to do with Mohr circle. So if the rule is, if both principal stresses, okay, so this is assuming that you have a plane, all right, plane stress, plane stress. If they're both positive, okay, then what you do is sigma 1 minus sigma 2 divided by 2. Okay? For this xy, right? And we already did that, right? And for tau max yz, you just do sigma 2 divided by 2, right? And that's what we just did. And if we want the absolute max, then we just do sigma 1 divided by 2. So you could write this down and not write Mohr circle, right? And just put these equations down, okay? But I think Mohr circle makes this a lot simpler. Okay, now what happens if one of these stresses is negative? When I say one of these stresses, I mean what happens if sigma 2, okay, is negative? And this is, remember how I was saying that sigma 1 is typically greater than sigma 2, is typically greater than sigma 3? This is one of those cases where we're going to peg sigma 3 on the origin, and sigma 2 is actually going to be less than sigma 3, okay? We don't, this is, yeah, it's a little bit, but it is what it is, right? You could maybe say that the absolute value of sigma 1 is greater than the absolute value of sigma 2 is greater than the absolute value of sigma 3, maybe, okay? But typically sigma 1 is the most positive. So what happens in this case? Well, if we draw the Mohr circle, okay, it looks, right, there's the sigma 1, here's sigma 2, all right, and this is the Mohr circle. What is the third principal stress? Well, if it's like what we're talking about, where sigma 3 is equal to 0, okay, or sigma z is equal to 0, then we're gonna peg another stress at the origin, okay, and we can start to look at these different planar states, okay, same thing we just did, where we rotate. Okay, about different axes, and we see, oh, in this case we just have sigma 1 and a 0, so that gets there. And in this case we just have a sigma 2, right, which is going to give us this Mohr circle here, okay, with the 0, all right, and we get these. So in this case, right, if one is positive and one is negative for a state of principal stress in a plane, okay, assuming that sigma 3 is equal to 0, we just use the maximum in-plane shear stress for the 1, 2, or in this case, x and y. Okay, so there's no difference between the absolute maximum shear stress and the maximum in-plane shear stress, at least in the xy plane. Okay? All right.
Is that case like for I-beam?
Okay, good. Okay, so Chris, is this only for I-beams is the question. All right. What we're talking about.
No, like the negative and then the positive.
Oh, is it? Oh, I see what you're saying. No, it's not only for beams. You can have other, right? Like I could just take this block of material, okay, and I could pull it in this direction while I'm pushing it in this direction, right? And that'd give me a sigma 1 that could be positive and a sigma 2 that could be negative. Okay, like this is not a great example because it's flimsy, but that's an example. Okay, so here's an example where we want to find the absolute maximum shear stress, and we're given a sigma x equals 100 megapascals, sigma y equals 50 megapascals, and the other stresses are 0. Okay, well, that's nice. That's a state of principal stress. Principal stresses, right? Because all the shear stresses are 0. So what do? We say sigma 1 equals sigma x is equal to something. All right. Can we once again kind of turn the volume down, please? Okay. Please? Thank you. Okay. Sigma z is equal to sigma y, okay, is equal to, sigma 2 is equal to sigma y, is equal to 50 megapascals, and sigma 3 is equal to 0. So what we do, we draw the Mohr circle, all right, and we we have just our two stresses on this first circle, right? 150, all right? So the 100 megapascal one here, the 50 megapascal one here. So we can go ahead and draw a more circle there. And this is kind of, actually these kinds of problems are kind of fun, to be honest, I think. Because you're just like, it's like kindergarten. You're just drawing circles, okay? So this is the XY plane, but we know that there's a third stress, sigma 3 equals 0, right? Which means that we got to put something here at the origin, okay? So yes, we can have fun and we can draw this YZ, okay, circle, but once again, we know that's not going to give us the absolute maximum shear stress. The absolute maximum shear stress is going to come when we draw the big circle, okay, between the sigma 1 and the sigma 3. Okay. The diameter, well, that was just 100 megapascals, right? And so the radius, that's the 50 megapascals. We go whoop down here, and voila, we're going to have a tau absolute max of 50 megapascals. Okay, pretty straightforward, right? Fun? Questions? Yeah? Okay. Go ahead and spend a couple minutes talking with your buddies, okay? And try to do the third problem. And there's a fourth one as well, okay? If you want to do that. Okay, 3 and 4. What are you saying, Zach?
So what I'm up against even just that square, how did you know that the XZ plane is going to cover the maximum shear? So intuitively, how do you understand?
You did it? You did it?
So. I don't know that square is
Like the
shear stress. That's what bothers me. Why is it not? Why specifically XZ?
Okay.
I had to go get something to eat. I was pretty hungry. I already finished it.
You did?
Yeah, that's a good question.
Yes, Kevin, yes.
More so a generalized question. Could you explain how you kind of set up the problem? So, for instance, how do you just know it's going to exceed like has the maximum shear stress and not an X, Y, or YZ?
So if I'm doing just because that's in this case it was given as
But specifically, why is it the maximum shear stress occurs on the XZ and not on the XY?
That's because we had to care about that sigma 3, right? That's why we do the rotations. We're looking at X like that. And that we have other constraints that we weren't thinking about.
So can you think about it as the largest shear stress is determined by the smaller constituent stresses that you have to worry about, and so like the larger final total maximum shear stress has to reach all of the other points on that.
Yeah, I would say the largest shear stress is from the biggest triple fusion off.
Yeah, so coming down, since Q1 are considered That makes the circle. So because sigma is 0 and sigma 1 is 100, that's what gives you the military space happening. That's what gives you the breakage.
That makes sense.
No. That's what he was explaining. I just don't.
No, but okay, that makes so much sense. Right. Okay, that makes sense. So,
Okay.
Yeah, I did.
All right. How's it going? Anyone that was working? Not going so well. What's the matter? Going great. Okay. Has anyone solved it that hasn't solved it before? For the first time? Did anyone solve it for the first time?
Using
Anyone?
the circles inside.
Yes. Question.
Because the first one gives you, that's a negative.
You got it? All right. Anyone else? Yes.
For this one.
Oh, in this
It's
case?
the absolute max.
Yeah. Yeah.
So this is when
Yeah. In this particular case, yes.
this is there.
Yes. Good. Okay. Your numbers are probably different. Your numbers are different. Yes, that's right. Okay. Now, the finale. All right. Good. We're good on time. All right. We're going to connect. All right. So now, if we can get back down, we can calm down again. All right. Yeah. All right, so now we're going to connect what we were doing to structures, okay? And we can look at, for example, a spherical pressure vessel, right? Now, you remember from the last homework, right? What was fun about the spherical pressure vessel? If you looked at the Morse circle before, what was it? For just the in-plane stresses. Huh? No, okay. It was a dot. Remember, because sigma 1 and sigma 2 were the same, right? So if we remember this, right, it was just this dot. Okay, and if you look at one of the previous exams, this was on it. Okay, it's just a dot. But now that we're thinking out of the plane, all right, how would you go about figuring out the absolute maximum shear stress? What is it? Is the absolute maximum shear stress 0?
Yes.
Why?
Because this is the tau axis and
Uh-huh.
the tau is 0.
Okay, yes. So I agree that the in-plane shear stress, the maximum in-plane shear stress, is 0.
Oh, so I can twist it.
Yeah. So what is the sigma 3 here? It's 0, which means we have another point on the origin, right? Which means that the absolute maximum shear stress is now this radius, and it's just PR over 14. Okay? All right? So that word in-plane maximum shear stress and absolute maximum, right? But if you see the absolute, then you got to think out of the plane. All right? If you don't see absolute, ask me, okay, on the exam, and I'll let you know. Okay, yeah, that's just in plane. All right? But you shouldn't have to ask me. If I say max in-plane shear stress, then that's what it is. Okay? So question 5 is doing a similar thing. All right? People wanted to ask about combined loading, so I think I'm going to spend time. I'm going to skip this one. All right? I think you got the general idea, because I think this is important. All right? People are like, how do I do the combined loading? All right? And if you you are still asking yourselves questions on how to do this, who are you going to call? Jeff Hansen. All right? Okay? If you don't like how I teach combined loading, just go watch the Jeff Hansen video. I'm not offended. All right? He has a nice video on combined loading. Okay? I think, though, that this technique is not bad. I think that the way we're describing it, but sure. Watch the combined loading sessions on from Jeff Hansen. All right, so here, what are the forces acting on this system? Good, all right? Py, px, pz, all right? And the location of interest is over here, right? Yes?
It's hard for me to understand based on these figures.
Uh-huh.
What's the actual location? Which plane is the plane of interest? Based on these
Okay.
numbers?
So A is at the most positive z direction portion of the geometry.
I mean, in the homework.
This
I mean,
this
here
is-
it says-
this is the
No,
homework.
No, but generally, it's really hard.
Yes, I agree.
Maybe here it's fine.
It's hard in general. This is the same drawing, okay? I agree. It's not trivial, okay? So I'm trying to be clear here, and I'm here now, so I'm telling you, right? A is at the most positive z direction. Remember, z is going to be x, y, or z equals x cross y, right? So z is positive coming out the back here. And A is on the back side, okay? And it's at the most positive z direction portion. Okay, so now we got to ask ourselves, how do we describe the stress? Okay, forget calculating the absolute maximum shear stress, okay? What we got to do is first describe the state of stress at A, and then we can start to think about what the absolute maximum shear stress is. So we're going to use the method of superposition, okay? All right, and this is a case, now I've said in the past, right, when you have equilibrium that you're doing on the triangle for a transformation, you've got to be very careful that you do equilibrium of forces. True. If you're at a location and you're looking at the stresses, okay, at that location, and you're very careful to make sure that you pick the same orientation of an element at that location for every stress or for every contribution of the different loads, then you can add those stresses together, right? So in other words, you know, if I have a uniaxially loaded beam, okay, and I'm pulling it apart, all right, and I got some normal stress, but then I apply a negative force, right, that causes it to have a compressive stress in the same direction, right? Then I can just add and subtract those normal stresses from each other, okay? So here what we're going to do is we're going to look at the contributions of these individual forces to the state of stress at this location A. Okay. And we're going to draw 3 circles, okay? Why do you think we're drawing 3 circles? These are not more circles, by the way. Okay, they're not more circles. Why are we drawing these 3?
For each one of the forces.
Yeah, that's right, right? We're going to try to look at what's happening at this point A due to each of these forces, Px, Py, Pz, all right? And it's nice in this case, well, right, it's nice that Px, Pz, Py, right, they're all in the positive x, y, and z directions, okay, the way we define it. Okay, so what we're going to do is we're going to look at the contribution from Px. Okay. We'll look at the contribution from Py, and we'll look from the contribution from Pz. Okay? And then once we've figured out what these contributions are, we'll add them all together. And that's superposition, right? Okay, so now you all tell me, Px, what is Px doing to this point at A? Or what is it, what point, what is it doing? Yes. Okay, all right, so px, right? Yes, it is, right? Good. What else is it doing? It's also, yes, it's applying moment. It's also applying what kind of stress when it has that moment? Okay, yes, Jesse.
Wouldn't it like compress into A?
Yes. Okay, it's going to compress A, right? Because this guy is going to be pulling out here, right? And it's going to be causing a bending moment at, like, you could essentially think about what's happening here. There's a bending moment going like this now, starting here, going like that, right? And if I look at my negative my over I, or however you want to look at it, or you just think of the deformation, it's going to compress this A. So you've got px doing a double whammy. It is pulling out, as we've pointed out, but it's also contributing a bending moment. What is the bending moment? What is the magnitude of the bending moment that px is applying? Exactly, px times b. That's the moment it's applying, okay? And so sigma x, okay, is going to have a px over a, right, which we just discussed, and it's going to have a pxb, right? This is the minus my over I. Yes?
From this reference, point A be on the neutral axis?
Okay, so you're talking about why is there no transverse shear, right? Or you're thinking maybe there should be transverse shear. Or you don't want to think about transverse shear. Okay, so there is, okay, so what you're getting at is this A at the neutral axis, okay? It's at one of the neutral axes, okay, but it's not at the neutral axis for this px, right? It's at the neutral axis for py, right? If the bending moment is applied in this direction, okay, all right? In other words, if there's a bending moment in the z direction, about the z direction, then it's at the neutral axis, and then it would be 0. Okay? This is confusing, okay? But because there's a moment pxb being applied about the y-axis, it's not at the neutral axis. It's actually at the top of the beam. There's a bending moment being applied, right? There's a bending moment being applied, right? And it's at the top, so it's going to be under compression. Okay? For px. For py, we rotate 90 degrees, and then it's at the neutral axis, and so there will be 0 bending stress. Y will be equal to 0. The effective y will be equal to 0. Okay. So, all right, so that's the sigma x. That's the stress from px. Now let's look at the contributions from py. Okay, so py is coming up here. Okay, and we're interested at point A. So what's happening? What is py contributing in terms of the state of stress at A? What's going on?
What is this tau t?
Well, that's a hint, yes.
No, t, but what's
Tau t is what I'm saying, that's a transverse shear stress. Okay, so there's a transverse shear stress. Okay? Or no, that's a twisting. Whoops! That's a twisting one. Sorry, I didn't even get straight. That's a twisting stress. Okay? So the twisting stress, Zach, you were going to say?
Providing a shear stress due to the twisting of the segment between the wall and
Yeah,
where
that's right. Okay? So that we can say that stress is going to be this one. Okay? And I got to go fast. And then there's a transverse shear stress. Okay, because remember the transverse shear stress is a maximum when it's on the neutral axis. Okay, So the max, and the way to calculate that out is just using 4/3 times tau average. Okay? But look, these stresses are in opposite directions from each other. Contributions from PZ. What's going on in PZ? Well, so no bending stress because A is on the neutral axis in this point. Sigma X, all right, from PZ. What's that mean? Okay, well, there's once again, okay, this can be pushing this way. This is going to be causing, right, there to be a negative bending stress, right, at this location. And there's no transverse shear stress because it's at the top. There's a moment about Y from PZ, okay? But that moment is going to be not contributing anything because it's at the top, okay? There's no transverse shear stress. Okay, so what you do is then you take, this is just exactly copied from the previous slide, all right? And you plug in your A, your I, and your J. And yes, you should write these on your formula sheet. Please do not ask me for these values during an exam too. Okay, I will say you should have these written on your formula sheet. Okay? The way I remember them though, at least I comes before J and I is less than J. Okay? All right, so then you draw the state of stress there, and then finally, after you've written all this out, you can work the problem to figure out what the absolute maximum shear stress is. And that's the problem. That's the answer. Or that will be the answer. Okay? So what did we cover today? We talked about triaxial stress. We talked about using Moore's circle to find the absolute maximum shear stress. And we did a couple examples on actual structures. Okay? I'll go ahead and put the attendance up. And then I want to do a demo while you're doing this. Okay. Whoops. No. Did it do it? Oh, it did it. Good. Okay. So I have a couple of breadsticks. Actually, there were one breadstick before. Okay? But I broke them on the way to work today. Okay? So it used to be one big breadstick. Okay? Now, what is this? This is a cantilever beam. All right? This is a cantilever beam, or I have two of them. If I put one in my mouth on this side, all right, and I pretend that my mouth is a wall, okay? And I apply a point load on this end. Okay, point load, let's say downward, upward, in, out, whatever. I apply a point load, and this is my wall. Where is it going to break? Will it break closer to my finger, or will it break closer to my mouth?
Through the finger, it's really thin.
Okay, yes, good point. So this is, assuming it was uniform, okay? Where would it break? Closer to my mouth. Why?
Because the maximum moment is there?
Yes, Kevin, that's right. Because you have, the wall can apply a moment, whereas my finger cannot. Okay, now I haven't tried this experiment. We're going to try it now, and we're going to see if this works. Okay, so I'm going to try to clamp down with my mouth. Oh, I don't think this is going to work. Okay, but I'll try, all right? Because it's going to go. Okay, so let me do it this way. I'm going to put my fingers like this, okay? And so the question is, where is it going to break? Now, you're right. It's thinner over here, so will it break here? How many think it's going to break closer to this finger? Okay, Daniel, how many think it's going to break closer to these fingers? Okay, let's see what happens. Okay, I'm trying to clamp. Ta-da! All right, physics, mechanics, all right? Because I was able to apply a bending moment with the wall here. Have a good week. Have a good Wednesday.
You should always begin moments, the top moments, with that exact thing, right?